My name is Scott Workman. I will be presenting our work titled Dynamic Traffic Modeling from Overhead Imagery. This is a collaboration with Nathan Jacobs. In urban environments, traffic patterns change drastically throughout the day. For example, in downtown Cincinnati, there is much less congestion in the early morning, shown on the left, versus peak afternoon, shown on the right. Here, traffic speeds are visualized as percent from free flow, where green indicates faster speeds. The goal of this work is to learn how to understand these types of traffic patterns directly from overhead imagery and associated metadata. There has been a great deal of work that tries to characterize traffic patterns at a location. One strategy is to estimate vehicle speeds by detecting and tracking vehicles in ground-level videos collected from traffic cameras. This approach is inherently limited as the coverage of ground-level videos is sparse. Other approaches require the road network to be known in advance and model individual road segments. The primary limitation here is that historical data is required for each segment, resulting in noisy predictions for segments with few samples. Instead, we explore how image-driven mapping can be applied to model traffic flow directly from overhead imagery, which is densely available. Extensive experiments show that our approach can capture complex relationships between the underlying road infrastructure and traffic flow, enabling understanding of city-scale traffic patterns without requiring the road network to be known in advance. This enables our approach to generalize to new areas. We propose a multitask convolutional neural network that operates on overhead imagery, location, and time. Our approach builds on an encoder-decoder style segmentation architecture with a shared encoder and separate decoder for each task. The objective of the first decoder is to segment roads in an overhead image, which we represent as a binary classification task. The second decoder estimates the likely direction of travel at each pixel and is represented as a multi-class classification task over k angular bins. The objective of the final decoder is to regress local traffic speeds, considering the imagery, the location, and the time. The output of our method can be considered as a local motion model that captures likely directions of travel and corresponding travel speeds. A key element of our approach for estimating traffic speeds is the integration of a region aggregation layer. Note that the ground truth traffic speed label for each road segment is represented as a single scalar value computed by averaging real-world observed traffic speeds. Instead of naively replicating this target label across the spatial bounds of a given road segment, we optimize for per pixel speeds such that the average over the segment matches the ground truth. This enables our approach to capture real-world properties of traffic speed, such as slowing down around corners or at intersections. To support training and evaluating our methods, we introduced the Dynamic Traffic Speeds dataset. Our dataset combines high-resolution overhead imagery with a year of traffic speeds for New York City, collected from Uber movement speeds. Visualized here are some example images from our dataset, shown alongside the corresponding ground truth road mask in the middle. The bottom row shows a speed mask rendered at a randomly selected time for each image. Notice that speed data is not available for every road at every time. This contributes to making our dataset unique and challenging. An ablation study explores the impact of our multitask approach. We've found that integrating the road detection and orientation estimation tasks into our architecture improves the resulting traffic speed predictions. Similarly, we conducted an ablation study to analyze the impact of integrating geotemporal context for traffic speed prediction. Our approach, which combines overhead imagery, location, and time, outperforms all baselines, including a metadata-only approach. Our approach can be used to create dynamic traffic speed maps at the scale of a city. Here we show predicted traffic speeds for the Bronx, New York City on Monday at 4 a.m. on the left versus Monday at 8 a.m. on the right. As expected, there is a large slowdown likely corresponding to rush hour. Our model is able to capture meaningful patterns in both space and time. Additionally, our method can be used to understand motion patterns in novel areas. Here, we visualize the predicted per pixel orientation for several overhead images overlaid as a vector field and colored by the predicted angle. As observed, our method captures primary directions of travel, including differences in one-way and bidirectional roads. Finally, our approach can enable many applications such as generating travel time maps. This visualization shows isochrone maps for Brooklyn and Manhattan that depict areas of equal travel time.